Welcome everyone to the 24th meeting of New Directions in Group Theory and Triangulated Categories. Today we have Jérôme Scherer from EPFL as our speaker, and the title of his talk is Floyd's Manifold is a Conjugation Space. Okay, over to you, Jérôme.
Yeah, thank you very much. It's quite an honor to be invited to this seminar. Thank you for putting this up, Radip. And yeah, last week it was Amnon Neyman, and now it's me. It's difficult to continue after him probably. So what I'd like to report on is joint work with Wolfgang Pitsch about this question we had for a long time. So for us, it's a long-standing question, and I know many people in the audience have heard us asking questions about this. In conferences, in seminars, at the CRM in Barcelona when I was there. So my plan is to start with a presentation of what conjugation spaces are, as Jean-Claude, who is there, has introduced them, and they've been studied by other people also in the audience. And then I will explain also how to look at them from another point of view, from stable equivariant homotopy theory. That's this joint work we had with Wolfgang and Nicolas Ricka. And then I will construct the Floyd manifolds. There are two of them, and take care in doing this construction equivariantly so that it can become a conjugation space, and then finally prove the title. So that was the plan. So let us start with what conjugation spaces are. So I think I will talk about conjugation spaces, but those are conjugation manifolds. You can work in more geometrical or more homotopical setting. So yes,
one very small comment, and if it's too much of too much of a trouble, like don't worry, like please ignore it. Would it be possible for you to make the color of the ink a little more dark?
Yes, maybe like this. Let's see. Tell me if it's better.
Yes, much better. Thank you. Thank you very much.
Much better? Okay, sorry for that.
No, I'm sorry for interrupting.
Maybe now I realize I've been teaching in light blue for a whole semester. Thanks. Okay, so here, so as I said, we follow this work by Jean-Claude Hausmann, and Puppe from 2004, maybe 2005. So let us fix some notation, and then I'll try to explain roughly what conjugation space is, and then give a precise definition. So for the whole talk, C2 is a cyclic group of order 2. And we consider, let's say, connected spaces with a C2 action. So I guess that inspired by classical examples, and here I will write down a single one, like the complex projective spaces, which have a conjugation action. Those three authors decided to check what is the nature of this space, which makes it special among spaces with a C2 action. So these spaces, so the spaces we will study will have mod 2 cohomology concentrated in even degrees, just like CPN. And there will be an abstract isomorphism, or maybe I should say halving isomorphism, because it will divide degrees by 2. And this they call kappa. So from the cohomology of this space with the C2 action to the cohomology of the fixed points. And we ask that it's an isomorphism, but just of graded vector spaces. There is no structure involved here. So this alone is not enough to ensure nice behavior of such spaces under various construction or anything. So we need something more to have a closer relationship between those fixed points, which for CPN look like RPN, real projective spaces. And the way they did it is the following. It's through the Borel construction. So we look at the Borel construction. Or homotopy orbits, which are obtained by taking a product with as EC2 as infinity with an antipodal action, so a contractible space with a free action, and then we divide out by C2, and we will write. We will use the notation for Borel cohomology with the H subscript C2 and by that we mean the cohomology of this Borel construction. So before giving the definition of a conjugation space, so notice that we have a fibration X HC2 fibers over BC2, and the fiber is X. And when we look at the fiber inclusion map, I star gives us a map from Borel cohomology of X to the cohomology of X. And here, for space reason, I didn't write down the coefficients, but throughout the whole talk, coefficients will always be in F2, the fields of 2 elements. Okay, so that's all we need to give the definition of a conjugation space. So now, if you don't mind, I will turn the page, and I hope that's okay for everybody. But yeah, tell me if it's too quick. So X is a conjugation space if there is a halving isomorphism kappa as above, a section sigma to the fiber inclusion in cohomology we've seen before, and there should be some compatibility. So let us look at what's going on here. We start with the class in the cohomology of X of even degree, and again I forget the coefficients, and we look at this section. So this goes to the Borel cohomology of the space And because I will compare it to some other Borel construction, let me write down what this is. This is X EC2 mod C2. And then we will use the inclusion of the fixed points in X. So the inclusion of the fixed point induces a map the other way around in cohomology. And because C2 acts trivially on the fixed points, this is just the cohomology of the fixed points times BC2. And of this space, we know how to compute the cohomology. This is the cohomology of the fixed points. And we take a polynomial algebra on a generator of degree 1, which comes from the cohomology of BC2 RP infinity. And this is in degree 2n. So if we start with the class here, then it should go to some class there, which has something to do with the data we have at hand. And there is one obvious class here. If we have X, then we have the corresponding class kappa of X in the cohomology of the fixed points. So this is of degree n. So if we want something of degree 2n, we better multiply by u to the n, which we have. And then this conjugation equation is that everything else is of lower degree. And I think that's something they write down, lower terms. So this is these lower terms is a polynomial in U of degree strictly less than n. So the leading term of this polynomial is kappa x times u to the n. And this is the definition of a conjugation of a conjugation space. And this polynomial, this special behavior of the polynomial in U is what they call conjugation equation. Okay, so that's the definition, and it might look like coming from nowhere, but just with that, there are super nice properties. So first property, they show that if such a pair, kappa sigma, a halving isomorphism and this section with the conjugation equation, if such a pair exists, then it's unique. If it exists, then it's not only a kappa. Let us focus on kappa. Kappa is not only an isomorphism of graded vector space, but it must be an isomorphism of F2 algebras. So it's compatible with the cup product. And then later, Matthias Franz, together with one of the authors of the first paper, just I think the year that this article was published, 1 year after that, kappa is also compatible with T-naught squares. And that we will see again in this talk later when I will talk about the Floyd manifolds. So maybe I should say that working on conjugation space with Wolfgang started when Jean-Claude visited Barcelona and was telling us about it. And yeah, then we read this article about T-naught squares, and we were intrigued about where it really comes from. And then there were these questions about realizability, which which spaces can be realized as fixed points of a conjugation space, and so on. So that's how it started. And maybe I should not forget Nick Kuhn's post on the discussion list top alge about those Floyd manifolds, because there was this intriguing pair of manifolds, which I will construct for you now or a little bit later, which look like a conjugation manifold and a small divided by two fixed points. Okay, so that's the story. So there is this way to look at conjugation spaces. Sometimes it might be difficult to verify the conjugation equation. So now I just want to present this other way we have to look at conjugation spaces through the eyes of stable equivariant homotopy theory. And this was Nicolas Ricka's insight, when he realized that what we are presenting here in this definition, everything is about cohomology, so it's stable. So let us look at another point of view. So my plan is just to give the basics and not go deep into the details of stable equivariant homotopy theory, even if the equivariant is just with respect to this little group of order 2, but still. So let me write down HF for the Eilenberg-MacLane genuine equivariant spectrum. Associated to the so-called constant Mackey functor. F, so just two copies of F2, one identity and one zero map. So that's the Mackey functor, and that's the Eilenberg-MacLane spectrum, which equivalently replaces the classical Eilenberg-MacLane spectrum with coefficients F2. Oh, F2, yes. So this is F now might be shorthand for F2. Okay, so non-equivariantly, when you smash a space with an Eilenberg-MacLane spectrum, then it splits as a wedge of suspended of a wedge of Eilenberg-MacLane spectra. Non-equivalently, this is more delicate, but in this setting we will have splitting, and I will refer to the theorems here. But so let us call now. Let us define. So a space, a C2 space, X is pure if X smash this Eilenberg-MacLane spectrum splits as a wedge of suspended copies of this Eilenberg-MacLane spectrum, and the suspended copies will be along the regular representation. So where rho is 1 plus the sign is the regular representation. Okay, so now you've probably guessed the theorem we proved with Nicolas and Wolfgang is that if X has finite type, then X is a conjugation space if and only if X is pure. And yes, maybe I didn't write down too many examples except CPN, but in the original article about conjugation spaces, there's a whole family of conjugation space which they call spherical, which are constructed using open balls in C to the n with conjugation action. And if you construct like a CW complex using equivariant attaching maps from those cells, then you get always a conjugation space. And so when you smash them with an Eilenberg-MacLane spectrum of the type I used here, associated to this Mackey functor, then they will split the way they have to, because from the geometrical way you constructed them. But what's maybe more surprising is that it always happens for a conjugation space, and this follows from the conjugation equation. Okay, so this was the end of section 1, and yeah, I don't know if there are any questions at this point that before I move to Floyd manifolds. Then if anything was unclear or someone would like to have more examples, then I could take questions now, but not necessarily. Okay. So let me continue with Floyd's manifold. So this construction goes back to 1973, and this work of Floyd followed Adam's work on Hopf-invariant 1, which solved the question of how many spaces or manifolds can you construct with only 3 cells, a point. So yeah, maybe let me write that down. So Adam's question solved the problem of how many manifolds can you construct of this form with attaching an n cell to a point, which gives Sn, and then adding a 2n dimensional cell. And Floyd looks at manifold with few cells, but more than that. And he actually manages to prove that there are only 2 non-trivial cobordism classes of manifolds with 4 cells. So if yeah, I never know if it's 3 or 4, but counting the base point, then it's 4. And so they have the following form. There is a point, and we attach a k cell. Then we attach an n minus k cell, and finally another n cell. And they live in dimension 5 and 10. So, and I will call them F5 and F10 for the 5-dimensional and the 10-dimensional Floyd manifold. So I will now explain how he constructs them, but he constructs them non-equivariantly. So on F10, then I will pay special attention on, through the whole construction, adding a C2 action, so that in the end, this might be a conjugation space. So let's review his construction of F10, and then the fixed points will be F5. So I will say what F5 looks like, but I will concentrate on F10 with a C2 action. Okay. So let us start with the following manifold. And so this is not a universal cover, it's just another 10-dimensional manifold we start with. And this is called F10 Tilde, and it's constructed as follows. We take the 3 sphere, which is the unit sphere in C times C. And on this 3 sphere, we have an action of S1, which is the unit sphere in the complex numbers. So that explains the action of the circle on S3. And on H, we look at H as being a direct sum of C with basis 1 and I, and then multiplying by J, we get J and K. So we split H into those 2 copies of C, and S1 acts only on the second one. So that's the way S1 acts, and that's how we then take the quotient of this diagonal action in S3 times HP3. So that's the S1 action, but now I'd like this to be a C2 space. So C2 acts by conjugation on all copies of C you can see here. So on S3 as a subspace of C times C with the conjugation action, and on H, oh, I wrote HP3, but it's HP2, sorry for that. So yeah, HP2 is 8-dimensional, S3 is 3-dimensional. We take the action on the S1. This is a 10-dimensional manifold. So that's F10 tilde, okay? So
I have a little question.
Sure.
So the action on HP2, you think of HP2 as the projective plane in 3 copies of H, and on each of the 3 copies,
yes,
S1 just acts on the second thing. Okay.
Yes, exactly.
So it's like 3 copies of that representation or something like that. Got it. Okay.
Yeah. Yes. There might be other models, but that's already what Floyd does. Maybe shifting the J on the other side, but we decided to do it this way. And so the only thing we added here is the conjugation action on every copy of C. But yes, that's correct. S1 acts on every copy of the quaternions. So when we look at the fixed points on the C2, then maybe let me write that down on the next one. So F10 tilde C2 fixed points. So here we are left with a circle in S3 and an action of the fixed points in S1 on a copy of CP2 sitting inside of HP2. And this is F5 tilde, the one could start with to build the smaller Floyd manifold. What else? We have a fibration, which I will use. In the middle, we have F10 tilde. We project onto S3 mod S, this S1 action, which gives us S2, and the fiber is HP2. So from a general result about vibration in the Hausmann-Holm Puppe article, we deduce from this that F10 is a conjugation manifold. And yeah, the cohomology looks just mod 2 cohomology looks just like this. There is one class in every even degree all the way to dimension 10. So now the next step is to get rid of this class, and then by duality we will also get rid of that class, and we will be left with something which is looking like what I promised, with a 0-dimensional class, 4, 6, and 10-dimensional classes. Okay, so that's the next step. We perform surgery on the following. So we choose. So this vibration is split because there is a fixed point on the S1 action on HP2. That was one handy reason to let S1 only act on one half of H. So we choose a section S of this vibration and consider a tubular neighborhood. Of this two-sphere in F10. And what Floyd shows, that the normal bundle to S2 in F10 tilde is trivial. And now what we need to perform this surgery equivariantly, so we need it to be so C2 equivariantly. So let me explain how we do that. So to do that, we apply a theory developed by Lück and Uribe about equivariant classifying spaces for equivariant bundles. So here, so such a classifying space, well, it depends like usual on a group of transformation, and here we will just consider GL8 on 8-dimensional fibers. But it also depends on a group which is acting on those spaces we are considering, and this is here C2. And it depends on a class of a family of C2 representation. So the classifying space, the notation, because there is only one here, in their paper, they specify also this family, but I will not, but I will say on which family it depends. So the classifying space, I will write BC2GL8 of R. So it depends on those ingredients inside the parentheses, but it depends also on a family of C2 representations. Namely, looking at a point an isotropy subgroup, we will have two kinds of representations. If we have a fixed point, then the isotropy group is trivial and we have the trivial representation. But if we have a non-fixed point, then we have a representation alpha of C2 in GL8R, which sends the generator. Well, this looks like in H times H, where C2 acts. So this looks like the identity matrix plus minus the identity matrix, and we use this diagonal 8 by 8 matrix. So this is the family of C2 representations which appear in this setting, and they allow to construct such an equivariant classifying space. So now the nice thing about the theory is that the normal bundle is trivial, and we will then be able to perform surgery if and only if the classifying map, let's say F, from our 2 sphere, which is a representation sphere in the base space with the action of C mod 2, and this bundle is classified by a map into this classifying space for an equivariant bundle, and the normal bundle is trivial if and only if this classifying map is null homotopic equivariantly. So let us see how to understand that indeed this map is null homotopic. Okay. So first, when we take the fixed points, this is a map from the equator, the fixed point on this representation sphere. And because it's an equivariant map, this maps into the fixed point of this classifying space. Lück and Uribe also determine the homotopy type of those fixed points, of those non-equivariant spaces which appear in the construction. And here, this is just the classifying space of the centralizer of one of those representations I had before. So you compute this and see it's BGL4 times GL4. So this is an element in pi1. Pi1 of this classifying space is Z mod 2 times Z mod 2. So it's not always trivial, but Floyd showed that the normal bundle was actually twice a bundle. And that's how he concluded that being 2 times something in Z mod 2, it was 0, that it was actually, that the tubular neighborhood was trivial, S2 times D8. So now we apply here the same argument. Twice something in Z mod 2 times Z mod 2 is 0. So we know that this map is homotopically trivial. So then that means that we can fill in this representation sphere, we have this equator. So now we extend our map F to construct a map G, which sends the not only.
I have another
Yes.
question.
Sure.
In that last argument, do you need to know that your normal bundle is twice an equivariant bundle?
So now at this stage, I only used what's going on the fixed points. So it's just a restriction of twice a non-equivariant bundle.
Okay, okay.
So at this moment, I haven't yet used C2 equivariant things.
Oh, is this something he would have used to construct his F5? Never mind.
I don't know.
Okay, yeah, never mind.
Yeah. Okay. So yes, so we can fill this. Not only the equator is sent to the fixed points, but we fill the whole equatorial disk and send it to the fixed point. So the whole part I drew in red now. This is sent to the fixed point of these classifying spaces by this argument. So now this space is equivariantly homotopic to S2 wedge S2 if I contract the equatorial disk, and the action of C2 flips those two wedge summands. So this is a free C2 space, and my map G can be seen as a map from this free space to this equivariant space, and by the free forgetful adjunction, we are left studying S2, the space out of which we constructed this free C2 space, to the classifying space, but where we forget the action. And this Lück and Uribe also identify for us. This is just BGL8. And this map is exactly Floyd's classifying map. So this map classifies the non-equivariant normal bundle. And it's trivial by Floyd's computation. And so therefore, that means that we can extend F, which was defined on a representation sphere, to the whole ball. And by what I said before, this means that the equivariant bundle is trivial if this map is equivariantly null homotopic. Okay, so this was the part of the argument where I tried to give some indications about how it goes, because that was also the longest, that part which took us longest, because for many years we thought that this normal bundle was not equivariantly trivial, but we didn't know at that time about this nice theory of Lück and Uribe. So let's do now equivariant surgery. So we define F10 as being this manifold F10 tilde. We cut out this equivariant normal bundle, which is trivial, and we glue back, d rho plus 1 times S 4 rho minus 1 along their common boundary. And this is F10. So the cohomology, as I said, the cohomology of F10 with F2 coefficients, this looks like this. Well, there is a class of degree 0, a class of degree 4, a square 2 here, a square 4 there. That's the cohomology of F10. And if we had done that non-equivariantly on the small manifold, where there is no C2 action left anyway, then we would have seen exactly what a halving isomorphism would have done to that cohomology. And the whole structure had already been identified by Floyd. So the cohomology of F5 with F2 coefficients, this looks like this. There is a square 2 from the top class to that one, and then a square 1 to the 2-dimensional class. So not only there is a halving isomorphism, but it respects the cup product, and it also respects the Steenrod operation in the sense you can guess from this picture. And this was the result by Franz and Puppe I mentioned before, which they proved for any conjugation space. So all in all, this looks really like the shadow of a conjugation space structure on F10. So that's now that we've done the effort to perform the construction of the Floyd manifold with a C2 action all along the way, now we are able to prove the following, that F10 is a conjugation space with fixed points being F5. So maybe this part of the proof is maybe less interesting, but let me just give the key ideas. Is that there is one important result, is that by Clover May, a recent result saying that for a compact space, when we smash with this Eilenberg-MacLane spectrum I introduced before, then this always splits. Of course, the summands that appear need not be of the form expected if the space is a conjugation space, but knowing that it splits, it becomes easier to prove that it's a conjugation space, because it means we only have to identify the summands. So we only have to identify the wedge summands. And going through the surgery step and knowing, starting from the fact that when we have F tilde, that we know was a conjugation space, so we know this one splits as a certain number of copies of suspended copies of HF of this Eilenberg-MacLane spectrum along representation spheres for n going from 1 to 5 to the 10-dimensional sphere. So knowing that, we finally identify those that are left after the surgery step, namely the one which are expected. So there is a 4-dimensional sphere, a 6-dimensional sphere, and a 10-dimensional sphere. Because it splits this way, we use our recognition principle or characterization of conjugation spaces that this must be a conjugation space. Okay, so that's the end of the talk. Maybe I can just end on a comment, which was a consequence we already knew before, but still maybe it's interesting to those who haven't thought about these spaces before, is that F10 cannot be realized as fixed points of a 20-dimensional conjugation space. Because Floyd showed such a space cannot exist. So just like because of Adam's work, the octonionic projective plane cannot be realized as fixed points of a 32-dimensional conjugation space by work of Adams. F10 is up to now the smallest manifold we know cannot be realized as fixed points of conjugation space. And maybe I should stop here. Thank you very much for your attention.
Thank you, Jérôme. Can we all unmute ourselves and give the speaker a round of applause, please? It's now time for questions and comments. If you have a question or a comment, please unmute yourself and speak, or alternatively, write in the chat.
So Jérôme, that's a very nice talk, very beautiful result. I wonder, in the surgery step you're doing C2 equivariant surgery on a manifold with a middle dimensional fixed set. And that's a case which has been studied by the people working on equivariant surgery. I'm wondering if your technique says something about the equivariant surgery obstruction group in that case, because you're able to carry out this explicit surgery.
I must say I don't know, but that's a very good question. We tried to attack this problem from different perspectives, and in the end, yes, we completely forgot other possible ways. Yes, that would be interesting to look at.
Thank you. Thanks again for the question. Any more questions for Jérôme?
I have a question about your general theory. You have this sort of characterization of these conjugation spaces as things that split after you smash with this Eilenberg-MacLean spectrum. Now, you also said earlier that that a conjugation space and its fixed points, I guess you said their algebra structures were the same, coproduct structures, and so I guess if I can use the language, I guess you're saying that cohomology of the bigger space is the double of the unstable algebra of the top. Now, algebra structure isn't really a stable thing normally. So can you, if you just started with your definition as a definition of a conjugation space, could you see all these algebraic properties? Could you see that the cup product is related in that way?
Yes, actually, in this article with Nicolas Ricka and Wolfgang Pitsch, we derive all the properties the original papers did from this perspective. The only one for which we don't have another way to look at is the uniqueness of this conjugation frame kappa and sigma, which we just I think if we wrote down something, then we just copied from the Hausmann, Holm and Puppe paper. But then the other properties, you can see them in this stable structure using geometric fixed points, and maybe the most delicate one was the compatibility with Steenrod squares, because you need to understand something about equivariant Steenrod algebra. Okay. But yes.
I guess I should read your paper.
Oh, if we could read all the papers we wish.
Thank you, Nicolas, for that question. Do we have any more questions for Jérôme? Well, while we're waiting for the next question, let me ask something that I was thinking about asking. So can you go back to your second page? Like there was this another point of view at the bottom of second page.
Maybe not.
Hello? Jeremy, you're muted.
Oh, Zoom went out just at the right moment. So
it's all right. I mean, my question was going to be about like at the end of your second page in the presentation, there was, you said another point of view, and then you mentioned that in the non-equivariant case, things get more subtle. And my question would have been, can you expand on that a little bit? But of course, without the page in view on the screen, maybe that's a difficult question to answer.
Yeah, I don't know. I can share again, but I don't think it's necessary. What I was meaning is that in general, smashing with an Eilenberg with an equivariant Eilenberg-MacLean spectrum does not produce a splitting in wedge summands. Now I don't have an example in mind. The only spaces I've worked with are C2 equivariant, where we have this result of Clover-May. So at least we should look for non-compact, non-finite equivalent CW complexes to find a counterexample, which I don't have right now. And maybe with other groups acting, you can find even, I think, compact counterexamples to this general splitting. But yeah, I don't have examples now at hand.
Okay, thank you. Thank you very much for your answer. Do we have any more questions for Jérôme? Well, if not, let's thank the speaker again.
Bye, everyone.
Yeah, bye. Thank you for joining. It was good to see all those specialists about conjugation and other friends.
Thank you for the talk. Great to see everyone. Yeah. Bye-bye.
Yeah, bye.
We have a meeting next week. We have a talk next week by Martin Galauer, and then we'll break for Christmas. Yeah, thank you everyone for coming, and thanks again, Jérôme. It was really a wonderful talk.
Thank you all.
Bye.
Okay. Thank you. Yeah, thank you very much for the invitation. It's a fantastic seminar you have managed to